Great! That sounds good. Why is that? Because it's a Friday?
Actually, yeah, that's one of the reasons.
Okay, so, do you have any questions?
So have you looked at the test yet?
I have looked at the tests. Let's not ruin the weekend. So, I'm only halfway through them, but
How do you think we did?
horrendous. No, not horrendous. I shouldn't say horrendous. There's issues that I need to address, but since I haven't actually finished grading them, we'll talk on Monday about this at length. So no, there were some things that were nice and good. But as I said, we'll talk more about it, and it's kind of hard to tell considering I don't actually look at all everybody's scores or anything like that. I think I told you in the past I'm trying to be as consistent as possible, so I grade like the first page on each test, and I move to the next page on each test. So actually, I went an extra step this time. I graded both my sections in the same time. So I went through the first page on the all 100 exams, and then the second page on all 100 exams. So anyway, that's why it takes me a long time, because it's a lot of exams. Okay. I just realized as I was opening up the book today that I forgot to actually bring a new homework sheet.
Oh, bummer.
I know, I'm sure everybody's very sad. So what I will do is I'll put it on the website today. Yeah, well, I mean, I wouldn't want you to be bored the whole weekend. I mean, I heard tomorrow's like, gonna be in the 60s, it's ugly, nobody wants to sit outside. I mean, you just, sit home and do math. Parents' weekend? Well, they can help you with the math then. I am obviously joking, but okay. So, any other thoughts? Yeah, the homework is going to be the same scenarios before. Yeah. So homework is going to be. There is really no, I guess to quote the postal offices, no rain, snow or sleet or whatever it was. The homework we'll do every Wednesday. Will be due every Wednesday. I just don't actually have the sheet, but I can tell you pretty much what's going to be on the homework. I mean, it's standard problems 2 through 40. Okay, actually I guess 44 and 46 as well. Okay, so, any other questions? Yes?
Can you print the homework sheets or write them on your website?
I will print them. Yes. What I'll do is I'll post them on the website. But what I'll do is I'll also print them out, and I'll probably give you the homework for the next period up until your next test. So it'll be probably another, the next 3 or 4 sets of homework, not just one. Okay. So new stuff. Or other questions?
I think we'll have more questions when we get our test back. Because right now, my question is, how well did I do?
My answer is I have no idea.
I know.
We'll find out more as we get there. My intention also, and we'll see how exactly it all works out, if I have the time to deal with all of this until Monday. But my intention was also that I would like to actually compute your grades up to the point on Monday. So I'll look also at your homework and quizzes and everything else and put it all together. And as I said, it should be relatively intuitive to compute it for yourselves. But in case you can't, then I can help you out. Remember how to compute your homework, your grade, at any given point? Everybody remembers?
It's 1,000, right?
Yeah, but that's not the way you're supposed to do it, because out of 1,000 is at the end of the semester. So what you need to do is you add all the points that you scored up to now and divide by the total number of points you could have scored. Everybody understands that? So for instance, first, the pre-test was worth 50 points, the quiz was worth 50 points, so that's 100 points, and then you had, 5 homeworks by now returned? Or 4? So 4 times 15, that's 60. So 160 plus the test was 150, so you're looking at 310 possible. So we basically are roughly a third into the grade so far. So, okay. So today we're gonna learn the last rule of taking derivatives. So after we complete today's class, we should have the tools to take derivatives of pretty much anything. And I'm saying pretty much because 2.7 deals with implicit differentiation, so it's the same rules, it's just that we're not necessarily going to look at functions, we're going to look at actually expressions. So we'll come back to that when we get there. Okay, so the idea is the following. And we had a problem like that actually in your test. But let's make one that actually looks a little more complicated. What happens if you want to take the derivative of the square root of x squared plus 1? Okay. For your test, the function you were looking at was actually the square root of 2x plus 1, right? Which I actually haven't gotten a chance to get to. I was on page 3, so I didn't get a chance to actually grade that, so I don't know exactly how you did. But the idea is, the only way you could have taken the derivative of this, which is one of the reasons why I put it in there, is just using the definition of the derivative. Otherwise, we had absolutely no way of taking the derivative of this up to today. Okay? And today we'll find out how you can take the derivative of this. Okay, so the key idea is the following. What's going to show up in the chain rule, and it's not suggestive in the title, but you'll understand why it's called the chain rule, is composition of functions. That's why we actually put an emphasis on composition of functions in the beginning of the semester. You were tested in the quiz and the test because they keep coming back to us. And so the idea is, can you come up with two functions, f of x, or let me call it in this fashion, f of, to really come back to the chain rule, f of u and g of x, such that capital F of x is f of g of u, g of x. F of u is the square root of u, and g of x is x squared plus 1. Yes? Remember these?
Yep.
Okay. Good, because that's what you're going to have to do for pretty much every single one of these problems.
Homework problems?
Yes. Homework and today. Okay, so the idea is, intuitively speaking, dy over dx can be viewed as dy over du times du over dx. If you want to think about it, even though this is not correct mathematically, but think about if you cross out the u's on the du's on the right hand side, you end up with the left hand side, right? Again, as I'm saying, that's not actually what happens, but that's kind of like what you can think of. Is that door open?
Yeah.
So okay. So what is the chain rule actually saying? And we're going to learn the chain rule in two different ways. So as it turns out, the chain rule is actually going to say exactly what I have written over there. Okay? But because we don't necessarily know what that means, let's actually introduce concepts first. So if f and g are both differentiable And capital F is equal to F composed with G.
You saying differentiable is something that's a polynomial that can be derived, I guess?
No, remember what differentiable means. It means it has a derivative. That just basically says that both of them, you can take the derivatives of both of them, and they make sense. Okay? Then, everybody remembers what fog is defined to be? F of g of x? Okay? So then, capital F is differentiable. And capital F prime of x is equal to F prime of g of x multiplied by g prime of x. Now, in Leibniz notation, if y is equal to f of u and u is equal to g of x, are both differentiable, then dy over dx is equal to dy over du times du over dx. Okay? Notice that this is exactly what we were just talking about earlier, right? So now let's come back to our original function. Capital F of x is equal to the square root of x squared plus 1. So the question is, what is capital F prime of x? Okay? And so the idea was the following. F of u we define to be square root of u. G of x is defined to be x squared plus 1. Right? When you put them together, you end up with capital F. So far, so good? Okay. What is f prime of u? Bless you. 1 over 2 square root of u. Right? And what is g prime of x? 2x. And so what is capital F prime of x? Remember, it's f prime of g of x times g prime of x. So it'll be 1 over 2 times the square root of x squared plus 1 multiplied by 2x. Does this make sense?
Yes.
Well, you look at f prime, you put in g of x instead of u, multiply it by g prime of x. Does this make sense? And so it'll equal x over the square root of x squared plus 1. Right?
Yes.
Wonderful. So let's look at more stuff. Example 2 sounds interesting, so let me go through that. Y equals sine of the quantity x squared. Your favorite functions. So what is the derivative of sine of x squared?
Negative cosine of x squared.
So let's take it on steps. Do you want, by the way, functions, or let me do it in this fashion and you tell me which one you prefer. If I denote with u, so let me how should I do this better? Yeah, let's do it this way. U equals x squared and y equals sine of u. Would that make sense? Then dy over dx is equal to dy over du times du over dx, right? That's what the chain rule says. So now, what is du over dx?
X squared.
2x. And what is dy over du? Cosine of u, right? And so what is dy over dx then? It'll technically be cosine of u multiplied by 2x, right? However, we started as a function of x, we had no u's, and so the next step would be to go back and replace the u with whatever it was. And so this is going to be cosine of x squared times 2x. Does this make sense? No. The key idea about the chain rule is we're going to integrate from outside in. That's basically differentiate from outside in. That's actually what we're going to do for every single one of them. Okay. What does this mean that we're integrating from outside in? Well, if you look at, for instance, the previous problem, okay, we had the square root of x squared plus 1. Okay. Integrating from outside in means the first function you can look at is the square root. What's the derivative of the square root function? 1 over 2 times the square root, right? Times the derivative of the inside function, which is x squared plus 1, so you end up with 2x. Is everybody seeing this? Point is, you could have 5 functions, one inside the other, and so when you take the derivative, you go from the outside function and you keep going in until you actually end up with the inside. Does that make sense? Okay. So out of curiosity, what would you guess if y is equal to, what was this? Sine squared of x. What would dy over dx be? Two sine x cosine x. Does that make any sense? Keep in mind that sine squared of x is nothing else but sine of x quantity squared. Okay? So again, taking it from outside in, the first function you're differentiating is the square function. Right? The power rule would say that's just 2 times the function to the first. 2 times the function to the first. Times the derivative of the inside function, which is cosine of x. Yes?
It seems like we're taking the partial derivative of sine squared of x. Like we're moving the 2 down in front of the sine, but we aren't changing sine into cosine. We are? Yeah, second term, how about the first term?
Y is equal to u squared. U is equal to sine of x. Right? If you put them together, you end up with sine of x quantity squared. Right? What is the derivative of u squared? 2u. So when you take the derivative, you end up with 2u times the derivative of sine of x. So you end up with 2 sine of x times cosine of x.
The dy over the dx part of it.
That's the Leibniz notation that tells you you're taking the derivative with respect to that value. So dy over du is technically the derivative of y with respect to u. So it is just 2u. Should I just go and do some functions? Some problems? Okay. Number 1, on page 119. To answer your question about how much work we need to show, problems 1 through 5 actually ask you to come up with f and g. After that point, you just take the derivative however you want to go with it. So number 1 says y is equal to sine of 4x. So for problems 1 through 5, we're supposed to identify the two functions that compose and come up with this function. So the idea is we need to write y as a function of u, and we need to write u as a function of x. Do you like it better with f and g versus y's? Yes or no? Does it matter? F's and G's? Or U's and Y's? Okay, let's keep this with Y's and U's since I started writing them, and then the next one we can do with F and G's. Okay, so Y is going to be sine of U, and U is equal to 4x. Everybody sees that when you put them together, you end up with sine of 4x?
We do y of u, right?
Y of x. Well, y composed with u, yes. So dy over du is cosine of u, and du over dx 4. And so what is dy over dx? Cosine of 4x times 4. Everybody sees that? Okay. Number 3 or number 5? Let's do number 3. Y equals, and here, since we're doing functions, I'll just start off with f of x equals, or capital F of x, I should say. Eventually I'll get it right. Capital F of x equals 1 minus x squared to the 10th power. So what is little f of u, and what is g of x? U to the 10th. And g of x? 1 minus x squared. So what is f prime of u? 10u to the 9th. And g prime of x? Negative 2x. Right? So then capital F prime of x will equal 10 times 1 minus x squared to the 9th multiplied by negative 2x. Yes? Okay, I guess I forgot to say something. I'll just do this because your textbook has it, and so I don't want you to go and look. What happened?
Then one last thing. Okay, I got it.
Wonderful. Okay, your textbook has this written as a rule, so I figure I'll just write it out as well, so you don't go home, read the book, and say, why didn't he actually mention anything about this? I don't necessarily know why we really have to have a formula for this, but nonetheless, this is the power rule with the chain rule, which basically is exactly what we just applied on the previous problem. It says the derivative of f of x to the nth power is equal to n times f of x to the n minus 1 multiplied by f prime of x. Okay? Alright, so let's look at number 7. It says capital F of x is equal to the fourth root of 1 plus 2x plus x cubed. So what is capital F prime of x? How about we write capital F of x as 1 plus 2x plus x cubed to the 1/4. Now you can use the chain rule, or you can use the formula I just wrote above. In the end, it's kind of up to you, but they're actually the same formula in the end. So it'll be the derivative of the outside function, which means I have stuff to the 1/4, right? So when you take the derivative, you'll end up with 1/4 times the stuff to negative 3/4 times the derivative of the stuff. Two plus 3x squared. Does that make sense? Yes? And how do we write this as an answer? What is our final answer? Two plus 3x to the squared divided by 4 times the fourth root of 1 plus 2x plus x cubed, quantity cubed.
Can I just write the stuff?
You can write the stuff to 3/4 if you want, yes. Okay?
So is the derivative of fourth root of x 1 over 4 times the square root of x cubed?
Fourth root of x cubed, yes. Okay. Since we're having so much fun, let's keep going.
That was one.
G of t is equal to 1 over t to the fourth plus 1 cubed. So what would G prime of t be? Minus the derivative of the denominator, which will be 3 times t to the fourth plus 1 quantity squared times 4t cubed divided by t to the fourth plus 1 to the sixth. Remember, the derivative of 1 over g of x is minus g prime of x over g squared of x. So g prime of t is going to be minus 12t cubed divided by t to the fourth plus 1 to the fourth power. Now, if this is not to your liking, alternatively, we can start off with g of t equals 1 over t to the fourth plus 1 cubed, and write that as t to the fourth plus 1 to the negative third. And now when you take the derivative, it'll just be minus 3 t to the fourth plus 1 to the negative 4 times 4t cubed. Which, shockingly enough, gave us the same answer. Does this make sense? And this ends up that, right? So, equality. Okay. How about 11? Y equals cosine of a cubed plus x cubed. So the question is, what is dy over dx?
So representing A is a constant.
A is a constant since we're asking for dy over dx, yes. And it wasn't a rhetorical question. Negative sign of stuff, so a cubed plus x cubed times 3x squared. Right?
What happens to the x?
What x?
Well, I just derivative of a, got 3a squared. Plus
Why is the derivative of a cubed 3a squared?
oh, a is constant.
X is my variable, y is my function, everything else is a constant.
So a just disappears.
Well, what's the derivative of 2? What is the derivative of 2?
0. And a is 2.
Well, a is a constant, which means it can be any number. But the key idea is it's not a variable.
Oh, okay, so.
Yes? Okay. 13. Y equals cotangent of x over 2. The derivative of sine of x over x? I don't know. Well, are you talking about derivatives or limits? Derivatives or limits? Are you talking about the limit as x goes to 0 of sine of x over x?
Is that what it is?
That is equal to 1.
Oh, that's what.
The derivative of sine of x over x, you actually have to apply the quotient rule.
Oh,
So they end up with x times cosine of x minus sine of x over x squared.
okay, so that was for limits x goes to 0.
So what is the derivative for 13? Negative cosecant squared negative cosecant squared of x over 2 times 1/2. Yes?
Yes. Boy, this is different stuff from like number 1 and 3, right?
Why?
Because we aren't.
The only difference is we're not actually writing out the functions.
Oh, okay.
So the only difference is now we're actually putting it all together into one move. As in, the key idea to recognize is you're differentiating from outside coming in. So derivative of cotangent, then derivative of x over 2, and so forth, depending if you have more stuff. As, of course, we will.
If we use the product rule, we're going to get the same answer.
You cannot use the product rule. The only thing you can use is the chain rule, because you have a function of a function.
That's right.
15. G of x equals 1 plus 4x to the 5th times the quantity 3 plus x minus x squared to the 8th. So now, if you really want to be creative here, you can technically multiply everything out. You'll end up with, what is it? 5 plus 16, a 21st degree polynomial that you can take a derivative of, and
Let's do it. I'm just kidding. No, no.
then again, I really think the next 2 hours could be, used differently. Yes.
So we do the chain rule twice then.
Well, yes. What you actually have to recognize here is what? It's a function times a function.
Function of function times function.
So the first key idea you should think about is product rule. Now, when you start taking derivatives of each of these functions, you'll end up actually applying the chain rule.
Oh, wait.
Yes.
Should we do the chain rule first on each one individually and then do the product rule? That seems like it'd be easier than doing the product rule first and then, let's go back and do the chain rule.
Well, how would you do the chain rule first without actually doing the product rule?
I'd do the 1 plus 4x to the big power. I'd find the chain rule of that. So I end up with the answer of something times something. And then I do it with the second term. And then I do the product rule.
But the problem is, if this is f and this is h, the product rule tells you that you're looking at f prime times h plus h prime times f. If you do the chain rule on both of them in the same time, you have f prime times h prime, which has no part in the product rule. Again, the key idea in all of these derivatives is you work from outside going in. Okay, that's actually the thing that you always have to recognize. And if you look at the outside, the first thing that you notice is that it's a product of functions. When you start taking derivatives of those particular functions is when you notice that they're actually composite functions. Okay? So what is g prime of x? Five times 1 plus 4x to the 4th times 4 multiplied by 3 plus x minus x squared to the 8. Chain rule.
Wait, now we're doing the chain rule. What? It's like we're rebounding back and forth.
Yes.
Oh.
Plus 8 times 3 plus x minus x squared times 1 minus 2x multiplied by 1 plus 4x to the 5th.
What'd you attach for?
Oh, to the 7th, yes, thank you. Chain rule. This particular quantity, that's why I'm using the brackets here. This particular quantity is the derivative of 1 plus 4x to the 5th. This particular quantity is the derivative of 3 plus x minus x squared to the 8th. Does this make sense?
Yes.
So you did 2 steps.
No. Why? I took the derivative. I just basically am saying the derivative of the first, so I wrote it out, times the second, plus the derivative of the second times the first.
It looks like you're doing the chain rule and the product rule.
Well, yes, because the product rule just tells you how to take the derivatives. It doesn't tell you what the derivatives are. So the product rule is not really, it's a rule of dealing with products of functions, but it doesn't necessarily tell you how to take the derivative of that particular function, right? If you think back to what we talked about, whenever we looked at the product rule, we either looked at the power rule, right? If I ask you, what would the derivative of, as an aside, of 2x plus 1 times x squared minus 3 is? Okay, so what is the derivative? 2 times
X squared.
okay.
That's plus 2x.
Okay. So you said you apply the product rule, right? How did you get the 2?
Just took it from.
The derivative of that, right?
Right.
Well, that's the power rule. It's not the product rule. When you take the derivative of this to come up with this, you're actually applying the power rule. So technically, you are doing two things into one. You're just not necessarily recognizing that there are 2 things into one. Because when you're taking the derivative, you automatically apply either the power rule, because that's the only thing we know how to deal with as far as polynomials, or you take the derivative of trigonometric functions, which we already derived. So you're always doing 2 things into one, basically. To not do 2 things into one would be the following. If I take the derivative of 2x plus 1 times x squared minus 3, to not do 2 things into one would be to say this is the derivative of 2x plus 1 times x squared minus 3 plus the derivative of x squared minus 3 times 2x plus 1. This is just actually applying the product rule that says the derivative of the first times the second plus the derivative of the second times the first. Is everybody understanding what I'm saying?
Yes.
And then the idea is, because we've learned how to use this a lot, we just decided that we're going to take the derivative directly without actually writing it out first. And so technically we are doing 2 steps at any given point. Same with the quotient rule. Whenever we say the quotient rule, we already take the derivative before we actually write out what it is. You had a question?
Yeah, let me scroll up a bit. Okay, the top right-hand corner, that little box, is that like the second part of the problem?
No, that was just
Or that's the equation?
just as an aside. That's why it's in a box and it's separate.
Is this what you want for Python? Do you want us to solve this out
Yes.
in the homework?
Chill. Again, what we're actually trying to do here, what we're trying to accomplish is, again, we're taking derivatives. Keep in mind that we're going to hit the next chapter, we're going to have to graph functions, okay? One of the key things that you were actually going to be asked is, when is the first derivative 0? Well, how am I going to know when the first derivative is 0 if I have it in this lovely creation? Second of all, what happens if I ask you for the second derivative? So, fear not, because things are going to be a little simpler. What I'm going to do is I'm going to erase the bottom row, okay? Because it's not part of the problem. It was just an illustration of things, and I want to actually still have the top while I'm still writing, so you can see what I'm doing. Okay? the same trick that we applied for the quotient rule will come into play here, in the sense that if you look at g prime of x, notice that I have 1 plus 4x showing up in both terms. What is the largest power it shows up in? Sorry, the smallest power. 4. So I can factor out a 1 plus 4x to the fourth. How about 3 plus x minus x squared? Again, it shows up in both terms. What is the smallest power you have? To the seventh. What am I left with? From the first part, I'm left with a 20 times 3 plus x minus x squared. From the second part, what am I left with? 8 times 1 minus 2x times 1 plus 4x. Do you see how easy this is actually factorable? Yes.
I got lost after 3 plus x minus x squared to the 7. What do we do to the rest?
I'm taking factors out as much as I can.
I saw that.
So I took out these out, right? Now go back to the first term. If you took out 1 plus 4x to the fourth, that disappears, right? If you took out this to the seventh, you're only left with 1, right? So what are you left with? Well, in the bracket, I'm left with a 5 times 4. That's a 20. Outside of the bracket, I'm left with 3 plus x minus x squared to the first. Move to the second term. In the bracket, the 3 plus x minus x squared to the seventh was factored out. What are you left with? 8 times 1 minus 2x. Go outside of the bracket. What do we have left? Well, we took out the 1 plus 4x to the fourth, so I'm left with a 1 plus 4x. And now all I have to do is actually just work out the algebra. I'll have 1 plus 4x to the fourth times 3 plus x minus x squared to the seventh times 60 plus 20x minus 20x squared plus 8 plus 16x minus 64x squared. Minus 2x plus 4x gives me 2x times 8, 16. So I did FOIL, but I also combined the, the inner and the inner and outer, I guess? Yes.
FOIL the last two terms on the right before you multiply this by 8?
Yes.
Okay.
Oh,
Okay? Bless you. So now g prime of x is 1 plus 4x to the fourth times 3 plus x minus x squared to the seventh times 68 plus 36x minus 84x squared. And so notice after a simple factorization how much the problem became, how much simpler the problem became.
It still looks ugly.
Well, we started with an ugly problem, so it's not going to look, well, a whole lot prettier, but the point is, now if I ask you when is the first derivative 0, you have 3 factors that you can look at, and you can easily figure out when that's 0. Does that make sense? Yes?
I want to know when it stops. Should we just not expand anything?
If it's already factored, you shouldn't expand it.
Okay.
That's actually usually the general rule. Okay. So having fun so far? You want 17?
Yeah.
Okay. H of t. Oh no, never mind. That's 16. I wouldn't want to solve your homework for you. Y equals 2x minus 5 to the 4th power times 8x squared minus 5 to the negative 3 power. And I have no idea why they wrote it in this fashion. Because that's a it's a rational function. Do you want to see it as a product rule, or you want to see it as a the quotient rule?
Why would that be quotient?
Because it's 2x minus 5 to the 4th divided by 8x squared minus 5 to the 3rd.
You get the same thing?
You should get exactly the same thing, yes. I don't know.
Let's do the quotient.
Quotient rule?
Yeah.
Okay. Big line. What goes on top? Because I got the hard part down. I wrote the denominator. Sorry? Four times 2x minus 5 to the 3rd times 8x squared minus 5 to the 3rd times 2. Never mind. I wanted to see if you're paying attention. I'll use brackets again so we remember what they are. So the brackets are the derivative. So far so good? Minus bracket 3 times 8x squared minus 5 to the 2nd times 16x multiplied by 2x minus 5 to the 4th. And no, you are not done. Bless you. So what can we factor? 2x minus 5 to the 3rd times 8x squared minus 5 to the 2nd. And what are we left with? 8 times 8x squared minus 5 minus 16 times 3 is 48 x times 2x minus 5. Right? So far so good? Yeah?
Instead of 48.
48, yes. 3 times 16.
How do you factor out the 8?
Sure. We can factor out an 8 as well. And also you can cancel out the 8x squared minus 5 squared with 2 of them from the denominator. Right? So we're left with 2x minus 5 cubed. And per your suggestion, I'll take an 8 out. So we're left with 8x squared minus 5 minus 12x squared plus 30x divided by 8x squared minus 5 to the 4th. Remember, if you take an 8 out, you're left with 6 here. Right? It's 6x. So when you distribute, you end up 6x times 2x, that gives you 12x squared. And then 6 times 5 is 30, so you end up with plus 30x. So far so good? So this equals 8 times 2x minus 5 cubed times negative 4x squared plus 30x minus 5 divided by 8x squared minus 5 to the 4th. In all its lovely glory. Or gory. Beautiful? Would you take it home? Okay. 21 on 119. Y equals sine of x times cosine of x. We haven't gotten to the more complicated ones yet, so you know. These are actually the simple ones. I know how to brighten your day, right? I guess it is Friday. I can't really. Okay, so what is the derivative? Cosine of stuff? Times what do we notice in the parenthesis? A function times a function.
Oh no!
So it'll be, I said it gets more complicated, so why would it be so simple to just 1 times cosine of x minus x times sine of x. Product rule.
Yeah, that's good.
The derivative of cosine is?
Oh, negative sine.
But so now if we go back a couple of steps, aren't you happy this was not on your test on Wednesday? Of course it's going to be on your second test. Actually, it's not that hard. It makes it off a lot simpler. As soon as you start working out with things, you'll see how things actually are simpler. 23.
Oh, that's it? That's it.
That's it, yes.
I never know where to stop.
Capital F of z is equal to a big square root z minus 1 over z plus 1. You'd really enjoy this one. We need a new page. So, now, by the way, now do you understand why I said the derivative of square root of x is 1 over 2 times the square root of x? And I'm just not going to go through it again over and over again, because it'll show up so many times in just a little different variations, but nonetheless it'll just keep showing up. So, 1 over 2 times the square root of z minus 1 over z plus 1 times the horizontal line. Z plus 1 quantity squared, z plus 1 minus z plus 1. Fine. Z minus 1 in parentheses. The derivative of z minus 1 times z plus 1. So 1 times z plus 1 minus the derivative of the bottom, which is the derivative of z plus 1, which is 1 again, times the top, which is z minus 1. So the z's cancel, 1 plus 1 equals 2, right? Can I simplify that with the 2 in front? Or is everybody seeing that or not really?
No.
Okay, never mind. Okay, this is equal to. How about if I say this is 1 over 2 times the square root of z plus 1 over z minus 1? times 2 over z plus 1 quantity squared.
Where does square root mean?
Yes or no?
No.
Okay, no.
No?
What, it's like
Fine.
square root.
Remember I told you need to know laws of exponents? 1 over the square root of z minus 1 over z plus 1 is equal to, technically, z minus 1 over z plus 1 to the minus 1/2. Right? That's just laws of exponents. Whatever you have in the denominator here, this is going to be that quantity to the minus the square root. Right? Still no?
Okay, let's go back up to the top. Scroll up a little bit. Alright. The top part I have.
Okay.
That
Okay.
in my head. Where did we get to the second part? What?
What do you think I'm doing here?
I have no idea.
Do you understand this equality? Yes? Okay, this is equal to, big bracket, parenthesis, z minus 1 over z plus 1 to the minus 1 all to the 1/2. Yes? What happens when you have the parenthesis to the minus 1? It's equal to z plus 1 to the divided by z minus 1 to 1/2. Raise it to negative 1 means you flip it. Yes? Are you just trying to make me feel better that you keep saying yes, or do you actually understand it? Okay. So that comes back to that, right? Now the second part, the only thing I did is I actually simplified the numerator. Z plus 1 minus z plus 1 is just 2 over the same quantity. Right? Now the 2 and the 1/2 cancel out. And what else can we do?
Take out a z plus.
I can split up the square root in having it the square root of z plus 1 over the square root of z minus 1, and the square root of z plus 1 with the z plus 1 squared ends up z plus 1 to the 3/2. Right? We did these types of problems in the test review, right? We had the square root of x over x squared, and you can write it as 1 over x to 3/2. Okay, let's see. Let me find one that's interesting. 29. $37 is interesting. But before I get there, 29. Y equals sine of the square root of 1 plus x squared. So what is the derivative? Cosine of what? Of the square root of 1 plus x squared. Keep in mind the one fundamental thing you should understand about every single derivative we've done so far. You never do two things in the same time. You never take two derivatives in the same time. That didn't work for quotient rule, that didn't work for product rule. So it for sure shouldn't work for the chain rule. In the sense that if I started with the derivative of sine, which is cosine, then I for sure have to leave the rest alone. I can't take two derivatives in the same time. It doesn't work for product rules, it doesn't work for quotient rules. It shouldn't work for the chain rule. Does that make sense? Okay, times 1 over 2 times the square root of 1 plus x squared times 2x.
But with the chain rule, I don't have to say.
Okay, keep in mind this is where the chain rule really comes into play as far as chain. We're actually looking at 3 different functions, so we're going to have 3 different derivatives. The most outside function is sine. The next function I go in is the square root. The next function I go in is 1 plus x squared. So you take the derivative of the outside function times the derivative of the square root times the derivative of 1 plus x squared. Is everybody understanding this? Okay. Let's see if we can find. Let's have some fun with 37.
Oh, is that it?
Yes.
I thought,
Well, the 2's can cancel and you can move the x
I thought
above.
we had to do the product rule. No, we don't.
Product of what?
It's not sine. No, that's right.
The square root of the argument of sine. 37. Y equals sine of tangent of the square root of sine of x.
Let's do it.
I love the enthusiasm. All right, what are we looking at here? There's 4 functions. Everybody recognizes that?
Yes.
You have the sine, tangent, square root, sine. So you should have 4 different derivatives multiplied with each other. Derivative of the outside function. Cosine of stuff. Right? Times secant squared of the other stuff. 1 over Now do you understand why it's called the chain rule? The idea is how you basically break it apart and you keep coming inside until you actually get to the end of it. Okay. Please do. Okay. And please don't have a thought about canceling this square root with that square root or with any other square roots.
Let's just
Yeah.
And this might sound like a thing, but you have no idea how many times I've seen in your tests that.
Wait, is that like log rules?
Not even log rules. There's no rule. That's just an imaginative way of getting around things, making up new mathematical concepts.
I don't even know if I did.
Okay. So problems 39 and 40, and I'm not going to do that because we only have like 4 minutes, and I want to do maybe 43 or 45. Deals with find an equation of the tangent lines, because we went through a whole class period without talking about tangents, so you knew that they should come out at some point, right? But we've done so many of them so far, right? The only difference is that the functions are going to be a little more complicated, so you need to apply the chain rule to take the derivative, but everything else follows exactly the same way. Okay? So
Something like that.
you have your function for homework will be sine of x plus sine squared of x.
So our homework's just 2 through 40.
Through to 40 plus 44 and 46. So homework is 2 through 40 and 44 and 46. And I should probably point out it's section 2.5. Okay, now let's do 43, which is similar to 44 and 46. Capital F of t is equal to 1 minus 7t to the 6th. And the question was, what's the second derivative? So we obviously have to do the first derivative first, and then do the second derivative. So what is f prime of t? Six times 1 minus 7t to the 5th times negative 7. Very good. So this is equal to negative 42 times 1 minus 7t to the 5th. Right? F double prime of t minus 42 times 5 times 1 minus 7t to the 4th times negative 7. Right? So what is that? My plus, let's see, 35 1470 times 1 minus 7t to the 4th. Is this making sense?
Yeah.
Are you're wondering how I came up with 1470? What you usually do is when you have numbers to multiply, you find a way to actually cheat and do it simpler. So what I did is I have 42 times 35. If you ignore the 2 for a second, you have 40 times 35. 4 times 35 is 1400. And then 2 times 35 is 70, so it's just 1470. Obviously, and it's Stuart's fault, not mine, 44 and 46 are actually much harder than this. Like for instance, 46 is actually tangent of 3t. So when you take the derivative, keep in mind that the derivative of tangent is secant squared. So when you take the second derivative, that's going to be secant quantity squared. So you have to apply the chain rule to that first. Okay?